Welcome to the Explainer. Let's jump right in. Today, we're going to completely demystify abstract mathematical formulas. If you've ever stared at an equation and felt like it was just a random, intimidating string of numbers and letters, well, we're going to shift that perspective today. We're going to treat these formulas exactly like tangible, everyday factory machines. We'll look at the raw materials going in, the gears turning on the inside, and the final products rolling right off the conveyor belt. Let's start with something incredibly relatable. Imagine you're standing in a store holding a $20 shirt that's on sale for 15% off. Your brain immediately gets to work, right? First, you calculate that discount. 15% off $20 means the shirt really costs $17. But you're not done. You then have to calculate the final cost after an 8% sales tax. So you take that $17, apply the tax, and figure out your total out-of-pocket cost is $18.36. You've just performed two distinct computations, one right after the other. Without even realizing it, you were chaining mathematical processes together. The output of your first calculation, that $17 discounted price, became the exact input for your second calculation, the sales tax. And that is exactly how composite functions work. It's not just some academic textbook theory. It's literally the fundamental logic that drives how we process sequential information in the real world. Okay, let's dive into this. Here is our roadmap for the Explainer today. First, the anatomy of a function. Second, domain, codomain, and range. Third, the rules of functions. Fourth, the power of composition. And finally, number 5, running functions in reverse. Section 1, anatomy of a function. Let's step right onto the factory floor and take a look at the basic machine. At its absolute core, a function is simply a process. It's a set of instructions that turns one thing into another thing. It points a member from an input set, which we'll just call set A, to an output member in set B. But there is a critical, unbreakable safety regulation in this factory. One-to-many is not okay. A single specific input cannot magically point to multiple different outputs. Think about it. If you feed a block of wood into a machine, it can't simultaneously produce a chair and a table from that exact same block at the exact same time. One input, one specific output. Section 2, domain, codomain, and range. Let's look at our inputs and outputs to see exactly where raw materials enter and finished products exit. To keep all this straight, there's a brilliant little mnemonic device you can use. Domain dives in, codomain covers completely, range is the real result. The domain is what goes into the machine. The codomain and the range deal with what comes out, but there is a really vital distinction between those two. To clarify that distinction, think of the domain as all your valid, possible inputs. The codomain is what outputs are merely possible based on the rules we set. For instance, we might declare our machine only produces real numbers. But the range? The range is the actual subset of results the machine literally produces when you feed the domain into it. To put that into perspective, think of a function that squares numbers. The codomain might be declared as all real numbers, but because squaring a number always gives you a positive result, the actual range is only the non-negative numbers. Section 3, the rules of functions. Let's move over to quality control to learn the strict mathematical rules our machine has to follow. We can actually visually prove a function's validity in a single glance using the vertical line test. When we look at a parabola mapped out on a graph, you can draw a straight vertical line down through it anywhere you want. Because that vertical line will only ever cross the line of the parabola exactly one time, it proves that for every x input, there is exclusively one y output. It passes the test, so we know for sure it's a valid function. Once we know it's a valid function, we look at how the inputs map to the outputs. We've got a few technical terms here, but they're pretty straightforward. An injective function, also known as one-to-one, means every input maps to a highly unique, exclusive output. No two inputs share the same output. Surjective, or onto, means every single possible element in that codomain we just talked about actually gets hit and becomes part of the range. And if a function manages to do both of those things, it's called bijective, a perfectly balanced one-to-one correspondence. But what does a failure of that one-to-one rule look like? Well, this is the horizontal line test. If you draw a horizontal line across a standard parabola, it crosses the graph in two separate places. So what does that mean for our factory? It means two completely different inputs, let's say -2 and +2, both result in the exact same output of 4. Because of that, this function is absolutely not one-to-one. It is an injective failure. Section 4, the power of composition.
Now that we've mastered the single machine, let's chain some machines together on an assembly line.
When you see the standard notation F, open parentheses, G, open parentheses, X, close parentheses, many students jokingly call it FOGX because of how that little composition symbol looks. But don't worry, we're not doing a weather report here. This notation is simply a set of visual instructions. It's telling you to take the entire output of machine G and plug it directly into machine F as its new input.
Let's think of this like a beer bottle factory assembly line. Machine 1, our inner function, puts the beer inside the bottle. Machine 2, the outer function, securely closes the bottle with a cap. If you compose these, you get a capped bottle full of beer. But notice the absolute golden rule here. These operations do not commute. You cannot reverse the order of machines on this assembly line. If you try to run machine 2 first and cap the bottle, machine 1 is just going to spray beer all over a closed glass bottle. Not great. So the absolutely crucial point here is that in mathematical composition, exactly like in our factory, order fundamentally changes the outcome. If function f is 3x minus 2 and function g is x squared plus 4, plugging g into f yields 3x squared plus 10. But if you reverse that and plug f into g, you get a completely different quadratic equation, 9x squared minus 12x plus 8. The mathematical products are entirely different. Order matters.
Section 5. Running functions in reverse. We know we can't easily swap the order of an assembly line, but what if we need to find our original raw material? Building a reverse machine is what we call finding an inverse function. And there's a really clean 3-step method to do this. First, you replace the f of x notation with a y, just to make the algebra a bit easier on the eyes. Second, and this is the real magic step, you physically interchange the x and y variables in the equation. You are literally swapping the inputs and outputs. Third, you just use basic algebra to solve for your new y. But remember our quality control tests from earlier? This reverse machine only works if the original function was 1-to-1. If multiple inputs gave the exact same output, the reverse machine wouldn't have a clue which original input to point back to. When you graph an original function and its inverse on the exact same chart, an amazing geometric relationship appears. The inverse function perfectly reflects the original function across the diagonal line where y equals x. That diagonal line essentially acts as a mirror. It's visual proof that you have successfully swapped your inputs and outputs. The domain of the first machine has literally become the range of the reverse machine. We've covered a ton of ground today, from the basic factory floor all the way to reversing complex mathematical assembly lines. But these concepts aren't just trapped on a whiteboard in some classroom. They actively govern currency conversions, physics, computer algorithms, and yeah, even calculating the discount on that shirt you want to buy. So I'll leave you with this. Look around your world today. What other hidden function machines are running your daily life right now, just waiting for you to unmask them? Thank you so much for joining me for this explainer, and keep learning.